of this multi-layer perceptrons, or you can say deep neural networks, how the training is done, basically optimization, regularization, and backpropagation. So to begin with, if this is what, just a minute. So this is what we learned yesterday, that this is your multi-layered network, and here you can see that we are learning the feature hierarchy. I gave you an example yesterday, and where we know that each layer is extracting features from the output of the previous layer, and important point is that all these layers are trained jointly, right? So up to this point, I think this is clear to everyone. Now, today we will talk about generalization, because what we want that our model should work good on the unseen data, right? So we are training our model, so and then we are testing it with the unseen data, and we want performance to be good. So so that is what we say generalization. So we want to know that how well your learned model is generalized from the data you are training to the new set of data. So here you can see that this is your training set with the labels known, and this is your, let us say, test set with the labels unknown. And generalization error is what determines model's ability to react to new unseen data. How your model reacts to unseen data, we want it to react in a good way. So let us discuss about model complexity and generalization. So the three pictures are being given to you, and here you can see that this is nothing but a simple two-class classification problem. And then here you can see that this is your simple model. Now here you are trying to make it somewhat more customized to, and then you can say intermediate model, and just look at here, such a complex. You want to classify each and every, it's too loud actually. You want to classify each and every instance of it, right? So if you consider so you can see that if you want to go to the third one, then the complexity of the model is increasing, right? If you move towards right side. So here, let us know that this generalization or test error of your learning algorithm is having two main components, right? One is bias, another is variance. So bias is what? Let us understand whatever I am going to discuss today. There are so many terms I am introducing to you, and you are supposed to know all these terms in order to successfully implement or understand the deep neural network, right? So here bias is nothing but error due to simplifying model assumption, right? So you are having a very simplified assumption, and that is how you can say that your model is not that good, right? So now, but what is a variance? Variance is actually error due to randomness of training set. So let us say you are training your model with one set of data, and then training it with some other set of data, and testing the how the performance differs over there. So here you can see that bias is nothing but how much the average model over all training set is going to differ from the true model. So once you have trained it over all training set and the average of that, so basically how it is working on the test data. So here always remember that if you are making simplified assumption, obviously it is prediction function will be easier to learn, but it is going to give you more error, because you are actually making too much simplified assumption which are not accurately representing your real world scenario. So obviously the result will not be as per the scenario. So here we can say that bias actually measures the deviation between the expected output of the model and the real value. So it actually tells you how much fit your model is. Then we come to the variance. Variance, as I told you, it is change in the estimation of the prediction function when you are training the when you are changing the training data. So once I'm let us say training it with X data, this result is there. I'm training it Y data, this result. So it is varying, right, with the change of randomness in your training data. So, and then what happens? So obviously we want to minimize this generalization error, but still something is there when you reaching the lowest bound of generalization error, and then you say that you are not actually getting rid of it. Why this is so? This is so because of noise, because your data, I mean, none of the system is, you can say, full, I mean, without noise. So every phenomena you are capturing, so we are capturing noise actually. Noise is there. So because of noise, you cannot have it below, I mean, certain level. So here you can see that this is your simple model. So in the simple model, your bias is high because, I mean, your model has, you have made too much simplified assumptions, and but the variance is low. But here you can say that so much, right? So this low bias is there. So remember what happens when your model bias is too high. When your model bias is too high, then what is happening? Your model is actually underfitting, right? It is actually incapable of capturing the important characteristics of your training data. And obviously, if it has not captured those characteristics of training data, how it will perform well to the testing data, right? No point in it, right? Now, when what happens when your variance is too high, right? So if your variance is too high, then your model is actually overfitting. And what happens that your model is also learning noise, right? And the unimportant characteristics in your data. You can see it is perfect, it is working well for the training, but because you are trying to fit it, right? Perfect. So it is not going to give you good results at the test time. So what is our problem? Our problem is that the challenge which lies in finding the optimal capacity. What we want both bias as well as variance low, right? So like keeping both low, that is a challenge. So how to do that? So because now the question comes that if I'm giving you this situation, so basically this is when you can see here high bias, so it is basically underfitting, that is your high variance, so overfitting. And so if I want to recognize whether whether it is underfitting or overfitting, so we need to look at both training error as well as testing error. So you can see that it is underfitting when your training error as well as test error both are high. But it is overfitting when your training error is low, right? At the training, like perfect, right? But it is not giving you good result at the test time. So that is what you say, that overfitting, training error is low, but test error is high. Now, remember that. So this is how you can say that underfitting and overfitting. You are trying to fit this green green one and this blue one, right? So always remember that if you are having model with too few parameters, that is also inaccurate because of large bias, because the model is not flexible enough to capture all the intrinsic characteristics of your data. But if you are using model with too many parameters, then there will be large variance. What does it mean, large variance? That your model is becomes sensitive towards the sample, right? So we want to make both low. So what is the problem? Let us understand there is a trade-off, right? If you want to deal with something, then I mean something is increasing, something is decreasing, how to keep both as low. So there is a bias variance trade-off, and here you can see that this we are showing you the result in terms of error and complexity. So at this end you are having high bias, low variance, and there low bias and high variance. So what happens here? This is your training error, right? So when you start training, then the training error goes on decreasing, right? Now, this is your test error, okay? So in the beginning, you can see the test error is high, but then, so it is increasing over there when you are having a model with low bias. So here you can see this stage is your underfitting, right? And this stage is your overfitting, because you can see that again, the error is reducing up to a certain point, and then it again starts increasing, right? It means that your model is actually overfitted here, right? So this is underfitting and this is overfitting. Now take this test error. So what happens if you are showing many training examples? So obviously your test error is going to decrease, and so here and if you are choosing few training examples only, then obviously at the test time your error rate is going to be test error is going to be increased, right? And so if you just take a fixed prediction model, let us say your parameters are all fixed, and now you are having a model over there, and you get what is the effect of the training size. So you can see that in the beginning, you can see when you started training why this error is less, because you are having very few examples and your model is overfitted basically, right? So, but then you are having this is how your testing error that decreases when you are increasing number of training example, and the gap between the two, that is there is generalization error. right? So we want to minimize this generalization error. So always remember that no matter n number of classifiers are there in literature, then no classifier is inherently, you can say, better than the other. You need to actually make assumptions to generalize it. And always remember that there are three kinds of errors. One is due to, I mean, inherent, you can't avoid it, due to noise. And second is due to bias, that is because of oversimplified assumptions about the model. Next is variance, because your model is not able to estimate the parameters from the limited data. Okay? So these are the three kinds of error. Now we come to the optimization. So optimization is a nothing but a process of finding. Remember, yesterday we are talking about parameters, weights and bias, right? So this is a process of finding the parameters so that we can minimize the loss function, right? Loss function or cost function. So now there are some strategies. The first strategy is you just go for a random search, right? Start random search. So you just try out many different random weights and just keep track like which set of random weights is giving you good result. But definitely it is a not a good approach. You can, it is understand. Now, second is that you are going for random local search, means that you are starting out with some random weights, right? And then you are generating small changes there. And so that based on those changes, you are just updating your loss. And so when your loss is going to be smaller, right, you are moving forward towards updation of weight. I gave you some examples also yesterday, how the weights are going to be updated when the loss is, so once you are your loss is up to the acceptable point, just stop over there, right? Now another strategy is this, that you can say following the gradients. So how actually you do that, how the weights are going to be updated, right? Here I'm saying that okay, you are updating the small weights, but how these weights are going to be updated? So let us follow the gradient approach, right? So because randomly there is actually no need to go randomly, right? But because you know that when where you want to reach, when you know that when you want to reach to let us say minima, or you want to reach to maxima, like you want to go down or up, so you know where do you want to reach, so there is no point in moving a random direction, right? You should move this your movement or you can say direction should be related to the gradient of the loss function, okay? Because that is going to tell you how you have to move. So let me show you that. So yesterday we talked about, we speak about gradient descent, but what is this gradient descent? So remember that neural network, when we train them, then they are actually being trained using iterative gradient based optimization process. And so that is how it gives me a solution, how it gives me a solution in the form of a cost function with very low value, right? Or less loss, you can say. So, and but then how we are going to apply gradient based learning? For that, we must be having a cost function, right? Because you are minimizing the cost, so we must know what is that cost function. So there are so now before coming to the that, let us talk about partial derivative, because yesterday we made use of partial derivatives. So here it comes, how basically what is the job of the partial derivative? They actually tell us how much one variable is affecting the other variable, right? And then so you can see there are two ways to think about it. Here we are talking about in terms of slope of a function, right? We are interested in, but we are already, so just to connect the things like with the whatever you know already, so you can say that knobs on a machine. So like there knobs on a machine, similarly I will tell you about slope of a function. So what do you mean by slope of a function? Basically you can, you know that the derivative, right? You know the two directions, so this derivative actually gives you the slope around the point, right? And if you consider this knobs on a machine, so nowadays, so some electronics student, they must be having those analog devices. But if you must have seen at your home these older devices. So here what is happening, your input and you are moving the knobs, right? So depending upon how much movement is there in the knob, the output is going to be changed, right? So here you can see that the small change in the parameter. So let us say there is a small change in parameter, and so corresponding to that, there will be a change in the in this gradient, right? So this is the derivative. Depending upon movement, how much weight you are putting over there, the derivative is going to give you, right? So you can see that how the knobs are affecting the output. Okay. So now come to the gradient descent, or you can say, so just for simplicity, we have taken just two weights, because if we are going for higher dimension, it is very difficult to visualize. Okay. So just take the case when we are having two weight vectors, and then based on that, I want to know the loss function. So remember that gradient always points, we all know that gradient always points in the direction of maximum. And if you want to, because we want to reach to the minima, so we need to go to the opposite of that direction, right? So I hope this point is clear. So given a fixed point on a function, right, you move to the opposite direction of the gradient, and sorry, you move to the opposite direction of the gradient, and then in this case you feel that with the promise that, okay, we will reach somewhere where we want to actually reach, right? So remember, when we have multiple dimension, here I just showed you two dimension, you may have multiple dimension, so your gradient is nothing but a vector of, you can say, partial derivatives along each dimension. So along dimension this W1 as well as in W2, and so it points actually towards the steepest increase of the function. You can take this example. So let us say this is your function, right? Now take the gradient here. So that is nothing but the derivatives with respect to x and with respect to y. Now if I want to know, see, let us say this is your point 4, 2, right? Oh, sorry, 1, 2. So if I want to know what is the gradient at this point, you can simply get it, right? So what happens that this function, so what we come to know that this function actually increases most rapidly in which direction? In this direction. And so where we need to go now? Opposite of that, right? So now is it clear to you? What do we mean? So just by two parameters it is being shown to you, and then you can imagine, I mean, multiple parameters there, and we are going towards the minima. So always remember that the slope in any direction, that is nothing but the dot product of the direction with the gradient, right? And so direction of steepest descent is the negative of the gradient. I hope this point is clear to everyone, because this is the most basic thing everyone should know when you are working there. So how we need to work here? See, so every step we are moving, right? So what is happening? We start with some initial estimate, and at each step you will find the gradient of the loss with respect to W, and then take a small step in that direction, right? So in the opposite direction you are taking it there. So you can see that what is your update rule? Update rule is nothing but this W is equal to W minus delta W. Right? So some small changes in the opposite direction of gradient. So now we know that we need to find weights as well as bias. So we are actually, so we are finding those weights and bias so that this loss function based on these weights and bias is actually minimized. So what we assume here, we assume that this loss function is a convex function, right? So we are saying, okay, let us say there it is having just one minimum, and that is where we want to reach. Okay? So that is there, and so we are going to proceed to the direction of opposite to the gradient, so that we can we can reach to this global, sorry, we can reach to this global minimum. Is it clear up to this point? Right? So this is your cost function, you can say the weight vectors, okay? Now let us see our incremental learning strategy, so or how the gradient descent work, right? So now let us say these are the several examples are given to me. So x1, x2, x3, they are input, y1, y2, y3, they are the output, and so we are having a single perceptron there, and this is your outcome, predicted outcome, right? So what is this? So we need to modify our weight vector, weight here you can say, such that your predicted output is closer to your true label. True label is y, predicted label is y hat, right? So it becomes closer. Now when we say closer, what does it mean actually? Right? When we say that your predicted output should be closer to the actual output. Right? So here you can see that is how to know this, we need to introduce this loss function. So as I told you, the neural network are usually trained using the iterative gradient based optimization process. And before we delve into the gradient descent, let us see loss function, uh, how we are defining this loss function, and what does it mean to be closer to the true outcome, right? So Now, see, these are the various examples of a loss function. So you can see that here, that is the difference between the, you can see difference between the true label and the predicted. So true output and the predicted output. And here you can see the loss. So this is your L1 loss. This is your L2 loss, hinge loss, 0, 1 loss. So here you can see that difference. If there is no difference, 0. If there is difference, 1. So we are going to use them depending upon the scenario. So usually L2 loss, let us say. Now, if I am saying that you need to code your perceptron. How you are going to code this? There are, so n number of observations are there, and what you are going to do here, you are updating your weight. And how you are updating your weight? This is the difference between your predicted and real multiplied by this input, and that is how you are predicting. So if you go for this, then it gives you just one line of code. And so, but how we are going to get on this, right? How we get this? So just imagine that, just remember, I just told you about gradient descent. And now I am telling you this is the weight update. So this is also a weight update, right? That is what we discussed. So what does it mean that actually this is nothing but the gradient descent? And what does it mean? Basically, this should be the gradient of the loss function. This means that this thing which we are talking about, this is nothing but the gradient of the loss function. Is it clear? Hmm? Now, so with this, let us assume what is our loss, because we need to link with all the things, right? So just see this gradient of the loss function. So let us assume that our loss function is an L2 norm, right? L2 loss. So here you can see, so the difference L2, I already showed you the difference and the squared one. So this is your loss function, right? Now, what is this? Now you know what this partial derivative is giving me. This is the partial derivative of loss function with respect to what? W, right? So what does it mean that this is the rate, this partial derivative of loss function with respect to W, that is the rate with which this loss is going to be affected, will change when you are going to change 1 unit, right, per unit of this weight, right? How? So this we are saying how the weight is going to be changed, and when your weight is going to be changed, how your loss is changing. You are just capturing the rate of that. So how you are capturing that rate? This is that rate, right? Partial derivative of loss with respect to weight. Clear? Hmm? Now, so now it means that we need to compute this derivative now. So when I'm going to compute this derivative, this is a very simple example. You know this, okay, so twice of this, then 2 are going to cancel out. This is there, and then d, this, because y cap is nothing but omega x. So you can say y by dw, so that will give you 0, and this is going to give you this, right? So this is how this minus sign is coming because of this, right? You are going to put this y hat minus omega x, so that is how the minus sign is coming over there, and this minus minus gives you. So this is what is there, that difference, right? So just in terms of shorthand, you can see I have connected the two things, right? I showed you the previous slide that how the weight update was there, that delta W, and now this is this, I said that that will be the gradient of the loss. So now I have connected the two things, and so we can say that what is this derivative is giving you? This is nothing but the effect of the weight on the loss function, right? When you are changing the weight, how it is affecting the loss function, right? So that is what this derivative is going to give you. Now, this means that if I am going to update the weight for the gradient descent, then I said that we need to move to the opposite direction of the gradient. So what is my weight update? W minus this delta W, and that is nothing but if you are going to put it here, just substitute. So this is my weight. And that is what we have written in the algorithm. Right? So how it has come, just to link all the pieces at the of the puzzle. So today we will put all the pieces of the puzzle on this right place, right? That is the. So here, see that algorithm, right, which I showed you for the perceptron. That is what I have written. And how I got this? I got it from this. So that is. Now, so if I am going to write the algorithm for this, let us say gradient descent, which is for the world's smallest perceptron. So you got this sample. Now in the forward pass, you are calculating the output, calculating the loss. Now you know what loss is there. Now based on this loss, you get this update, right? So that is the derivative. So here you can see. So now you need to, once you have computed loss, then you need to do the update, and for the update you need the derivative of the loss, and once you get the derivative of the loss, you have updated the weight, right? So just see these steps. You are going to, in your forward pass, you are going to predict the output, then you are computing the loss, and then what are you doing for weight updation? You need to know, do the basically back propagation, which we tell several times yesterday. And this whole progress is possible when we get this method, back propagation, for training our multi-layer perceptron, right? So here we got this derivative, and then you use that to update your gradient, and this is your update, and that is how you will move towards the local minima, right? So you can see, and this how this process will go on. This process, we need to update weights until we get the convergence, or you can say that until the difference between the two consecutive, like the values of this cost function is negligible. So see, we are not going towards keeping this zero, right? When we say, okay, it has become small enough, we have to stop, right? Till then, we need to keep on training it, right? Now, if we take this second example, when we say, okay, let us take two inputs, right? So we are saying, okay, this is a second smallest perceptron where two inputs are there. So your output, or you say it is a, or your loss function will be function of two parameters, right? W1 and W2. Now again, this is the same algorithm which I showed you in the previous slide. Now this algorithm is going to be, so how we are going to do? Now we are going to consider this thing for the two variables. So you can say that, okay, when we are going to do the back propagation and gradient update, we need to compute partial derivative of this network, right? Which is with respect to these two variables now, right? So here you can see that similar, like as I showed you this derivative with respect to W, now I have written it with respect to W1 and with respect to W2, right? Nothing, I mean, exactly same thing. Hmm? So now here you can see that how you are going to get it. Okay. So now when you are keeping it in the similar manner which we did in the last slide, what you are going to get, this corresponding to x1, this one is corresponding to x2. So this is nothing but your update in the weight vector w1. This is nothing but update in the weight vector w2. And now when, so what we are going to do with these partial derivatives? We are going to use these partial derivatives to update our weight vectors, right? So you know which direction you need to move, right? So you need to update your weight vectors. So we are going to make use of these partial derivative to update our weight vectors, right? Now when we are going to do update, there is a slight change, right, as compared to the previous slide. Here we have introduced a variable, we call it eta, right? Earlier what I said, W1 minus W2, right? This delta W2, but now there is a word come eta, and this eta is nothing but the learning rate, right? So this is a positive scalar that actually determines the step size, uh, uh, how you are moving towards the minimum, right? So if your step size is uh, basically that is your learning rate, and so if it is too big, there is a chances you can miss the minimum. But if it is too small, then your convergence will also be very small, right? Because you need to keep on running and just seeing how it is affecting the cost, right? So you can't move very fast, right? You can't move very slow. So this is one of the hyperparameter. Remember, we will discuss later, right? So just now. So now if you see this, what is changes, so till this forward pass, then now in the backward pass, what we are going to do, here instead of one line, now we are having two lines update, right? Because two weights are supposed to be updated. And then this is your this weight update, right? So just see here. So this is, and here you can see eta, that is, you can say that this is having adjustable step size, right? So you can adjust it by fixing the value of theta, right? So this is there. Now, now consider the situation when your samples, this time your sample just two features, but what if we are having n features, right? When you are having n features, then what happens? There will be, actually till now, we have not seen, although yesterday, I mean, in one of the, like we told you that, okay, this is how it works when you are doing back propagation, but we didn't do it, right? How it is actually going on, because our perceptron was having just one layer. Now here you can see, now we are having, just consider this multi-layer perceptron, where we are having 4 layers: input layer, hidden layer 1, hidden layer 2, and then your output layer, right? So you can see that this is your W1 bias, then W2, W3, and that is how Y. Now see what is going to happen. So this is how your, yesterday when I told you that how you are going to represent this network. So this is one way of representing it. Here you can see that this is your input layer. So layer number 1, that is your input. So here you can see that weight and bias, right? Now, what is your A1? A1 is nothing but W1, B1. Now, F1 is what? F1 is your activation function. Now you are passing this A1 to this activation function. What is your output? That is here, right? Now now the next layer you are reaching, the weight here is W2. Again, this is your activation function is this. The next is hidden layer, activation function is F2. Again, the next layer, the weight, this is having, this layer is having this weight W3, and that is how you are going to get. So here you can see this F1, F2, F3, they are the activation function. W1, W2, W3, they are the weight function. B is for bias. And now let us see how we are going to also, okay. So before moving, so these are the various activation functions. Sigmoid we showed you, and then ReLU. So usually, I mean, this is a good default choice because its execution is also, computationally effective. Now let us see what is going on here. And I would like you to pay attention, because once you will get this thing, then the whole thing will be easy to get, right? Now here, so what is your A1? I will go a bit slow here so that you may get good idea about this. What is your A1? A1 is nothing but W1 X plus B, right? Now move forward. So one step we are going to move forward. And when we are moving forward, what is your A2? A2 is nothing but W2 into F1, F1 A1, right? W2 into, what is this? What is the output here? F1 A1, right? So A1 basically is passed to F1, right? So the output here is F1 A1, right? So that is what you are writing here. So what is your A2? Your A2 is this W2 into F1 A1. Now what is A1? Just substitute here A1. Okay? Now let us move further forward. How are you going to write A3 now? A3 will become W3 into F2, and then what? This A2. A2 is what? This whole thing. Okay? Now further move. What is your this Y now? Finally, F3, right? So here you can see this F3. Then F3 में क्या pass कर रहे हैं? You are going to pass this A3. A3 is what? A3 is this. Okay? Output Y here is what? F3, A3, right? In this activation function F3, you are passing on A3. Okay? So here you can see activation function F3, and you are passing on this A3. This is your A3. Right? What does it mean? We started from this input X, and we wanted to reach there at Y, right? Output. It means that this whole network can be written with just one long equation, right? Just one equation. Okay? Everyone? Now we need to train this network. So we got this equation, and we need to train this network. Okay. Now here, what is known to us and what is unknown to us? So what is known to us? Only two things are known to us. That is X and Y. Rest everything, right? You can see all these weights, activation function, bias, everything is unknown, right? And sometimes your activation functions are also having parameters. Okay, so these are all unknowns which we have to learn. So now we come to the learning of multi-layer perceptron. So we are having this set of, so that is how, what is the way of writing here? You can say that this is the set of samples, and you are learning this multi-layer perceptron. So theta, right? We are saying whatever parameters I showed you there may be, like that was particular to mine, the network I showed you. Your network will be different, the parameters will be different, right? So we are representing it by theta over there. So let us say what are my parameters here? So we can say activation function, this F, W, and P. So learning consists of what? Minimizing the loss with respect to the parameters over the whole training set, right? These parameters, with respect to these parameters, we need to minimize our loss, and this too over the entire training set, right? That, okay, for this, maybe for maybe high, some may be low, but we'll say that overall for this set of parameters, my loss function, that is the best. So now here you can see that again we come back to our gradient descent algorithm. So we're saying, okay, now this time for each random sample you are picking up, then again your forward pass, the now we have written in terms of general form, that is with the theta. Now here you can see, so now we are having, earlier I showed you just one parameter, right? The derivative of the loss with respect to W1. Then we took example derivative of loss with respect to W2. Now I am saying that derivative of loss with respect to theta. Theta are all parameters basically, right? So like if there are 10 there, so I need those 10 derivatives, okay? And then we need to update, right? So that is why we are saying vector of parameter partial derivatives and vector of parameter update equations. Okay, so far so good. चलिए, now let us see that we need to compute these partial derivatives, right? Because without computing those partial derivatives, we can't do anything. And here there is a something where I want your attention. So let us say, so we are here when we say that derivative of the loss function with respect to theta, in this network, what are parameters there? So W3 is there, W2 is there, W1 is there, and B is there, right? So we need to compute all these, right? So derivative of my loss function with respect to all four parameters, and see how I am going to do that. Now, so remember when we say that, what is the meaning of this? When I am saying that derivative of the loss function with respect to weight W1 means that when we are changing W1, how the loss is changing, right? So we can say that this partial derivative is describe how this change of W1 affects this output, that is your at the loss layer, right? So the question comes, how we are going to compute it. So for computing it, we will not start from W1, but see, okay. So it means that there is a complicated function of parameters. So many parameters are there. We want to know what is the effect of W1 over there, what is the effect of B1, W2, W3, like that. And in reality, thousands of, right? Millions of perceptrons, right? Billions of new units are there. So how we are going to compute it? That is the question. And this answer we got in a very beautiful way, that is chain rule, right? So yesterday there was a mention to chain rule, that is nothing but a back propagation only. So let us see how this chain rule works. So this chain rule is a procedure to compute the gradients of the loss with respect to parameters in the multi-layer neural network. So let us say we are going to start from the end, right? So we are beginning from here because we are during forward pass, we have reached here. So now we will start from here. Okay. So now what my chain rule says that if I want to know what is the effect of the weight W3 on this loss function, right? I want to know the effect of the weight W3 on this loss function. So how I am going to get it? See here. So this loss function, it is going to depend upon F3. Now F3 depends upon A3, right? Output here. Now from A3, W3. So how I am going to write here how this W3 affecting loss function? We should write it in a reverse manner. You can say that derivative of loss with respect to F3 multiply by derivative of the loss with respect to A3, then derivative with respect to W3. Okay? And then we are saying, okay, at this point of time, we are here, and then we will gradually move forward. Okay. So now this is nothing but chain rule, right? So you are moving there, right? Now here, so we got this effect of weight W3 on the loss function, and now see how we are going to get it. See, loss function, we have decided L2 loss, remember, that is what we are following in this example. That is what we did the derivative in the beginning. I hope you remember, right? So here you can see that. So this is the nothing but this is the partial derivative of L2 loss, which I showed you also. So this is there. Now the next term comes, we need to know this partial derivative, this f3 with respect to a3. So let us say we decide that it is a sigmoid function, because activation function you need to decide. So let us say you decide that it is a sigmoid function, and now I know you can take the derivative of this, right? You know how to take the derivative of this, and just go and substitute this. Yahan pe this is with respect to x. I gave you example also. So now f3. So this is your f3, 1 minus f3. This is a simple thing. I hope I am not supposed to do that derivative here. And then this there, right? So now we can say that now, so when we say this derivative, this A3 with respect to W3, this is nothing but your F2, right? Because F2, it is coming from F2 only. So this is nothing but your F2, right? So you got this effect of W3 on your loss function. Now you need to get what? आपने कहां से शुरू किया था? From where we started, W1, W2, W3. So now you got the effect of W3 on the loss function. Now we should get the effect of W2 on the loss function, right? So let us see how. So now we are moving one step forward here. So now see here, this is your output, okay? And so see, this we have already calculated. So this now we want to know what is the effect of this W2 on the loss function. So you can see that here again the same chain is going to be followed. So y to this f3, f3 to a3, a3 to f2. Why we left this W3 here? See, when we are doing, we are saying from a3 to f2, f2 to a2, a2 to w2. Why we have left this w3 here? Because that we have already done. With respect to W3, whatever what was the effect of W3, that we have already done. So that is what we are not taking it here. So when you are writing here, just see this del L by del F3, del F3 by del A3, del A3 by del F2, like that. Okay. So good. Now remember this thing we have already computed when we are computing it, the effect of W3 on the loss function. देखिए यहाँ पे क्या what you did. See, this thing you have already computed. So something you have already computed, you need to just put it over there. Right? So you have simply, what you have computed, you have simply reused it, or you are saying it is a propagated, and that is what we say chain rule. Okay. So chain rule, or you can say back propagation, is an algorithm. Again, you can understand gradient of a compound function. You know now your compound function, right? I write it in just one go, and as a series of how we are taking care of it, as a series of local intermediate gradients, right? In terms of not, we are dealing with local gradients and step one by one. Now let us again move here. So finally we reach to W1. So W1, okay. So now remember that y to F3, see, sorry, this loss function is there. So loss function to F3, F3 to A3, A3 to F2, F2 to A2, A2 to F1, F1 to A1, and then A1 to W1. But they just have a look. And again, we have left W3 and W2. Why? Because we have already done, right? This we have already calculated, right? Now, see, now we know this has already been computed. When you are moving from backward, right? When you are moving from W3 to W2, then this is already computed. So we are going to reuse it, right? That is what is being shown by Steve yesterday, how this is being done. Okay. So when you are knowing, you can reuse it. Now just see, summarize everything in one go, right? This is what with change with respect to W3, with respect to W2, W1, and similarly like W1 and B1, same way, just in place of, in the last one, when it is saying A1 W1, it will become A1B. Rest everything will become same, will remain same, right? Now see, when we started from here, then this thing is computed. So when you are at this step, you can simply use it. Now when you are moving forward, I mean from the back side, what is happening? This thing is already computed, so you can use it here. Now, when you will move forward, this thing is again computed, so you are going to use it here. So that is what is called back propagation. That is what the example was shown to you with the derivatives, with the values, and here I am giving you the concept. So I hope this concept is clear now. Okay. So it means that what? That your back propagation will work with any. Remember here what is to do this back propagation? What do we need? We need partial derivatives, right? So it means that any activation function which can be differentiable, right? You can use it, and then your back propagation will work. So your any activation function which is differentiable, your back propagation is going to work, right? And also, but remember here, if you talk about the cost of the forward pass and cost of the backward pass, right? There is a huge difference. You see, the computational cost of back propagation is twice that of forward pass, right? It means that because why this is so? Because every step you need to compute gradient with respect to input and parameter, right? That is what we are doing now. We know that we are identifying with that which weight is what effect is there, and then all these things, because we said that all these layers, they are trained together. So now the changes, right? The changes are depending upon this, what you got as a derivative. You know this delta W1, delta W2. So these updates will be done. Once you will going to calculate this, see here. See here. Once you get this derivative, which I just showed you, then you are going to make use of this derivative to update the parameter. For example, you got this derivative with respect to W1, right? So you got effect of W1 on the loss function. So that effect is going to use to update W1. Got it? Then we calculated the effect of W2 on the loss function. So we need to adjust the W2. We need to adjust W2 based on how W2 is affecting the loss function. We need to update W3, how W3 is affecting the loss function. Right? That is what we are getting with this derivative. Okay, so based on these derivatives, we are updating. And how much we are updating? That is depending upon my learning rate eta. Kitne fractions hai, how much fraction? Because we can't take is too much, right? Too high, too low. So now I hope every I mean, the chain is, the chain is completed, right? The concepts are connected. So, so we were here. So computational cost, I was telling that back propagation is about twice of the forward propagation. Now, so you can see again our algorithm. So it is updated now for 4 parameters. You can see here. So again, you are calculating loss function, right? Then its effect, right, of all these parameters. And based on these effects, you are going to update these weights. And you are going to do it repeatedly till the whatever loss you is acceptable to you, right? That you will set before, this much loss is acceptable to me, and I reach it, I will stop, right? So we can say that it is nothing but this, because we are generalizing it. So we are saying, okay, this is a vector of partial derivatives. This is the vector of parameter updates. And so we can say that if we want to perform the gradient descent, it means that we need to calculate the gradient of the cost function. Right? We need to calculate gradient of the cost function, and to calculate the gradient of the cost function, what we need to sum the cost of each sample. See here, we need to sum the cost of each sample. Now here there is a catch. It means that, let us say you are having 3 million samples. Does it mean that you are going to loop through 3 million times to to use this dot product? Yes, if you are going for gradient descent. Every input must be seen by the in every pass. Every input you are giving to your machine, your network. Hmm? Is it? You need to give it, right? So if you are having, no matter how many parameters you have, you need to loop through these parameters uh, to get to use these dot product when you are going for gradient descent. So obviously there must be some solution, because we are not going to do that. Hmm? So remember, so the solution is what we say is stochastic gradient descent, right? SGD. But what is there? So I'm going to tell you about a couple of things here. So gradient descent and stochastic gradient descent, they update the set of parameters in the iterative manner to minimize the cost function. They are doing the same thing, but what is the difference over here? There, for each pass, you are showing, you are giving your input, your network, those 3 million parameters. In stochastic gradient descent, you will not do that. You will just give one or you can say subset of training samples from your training set to update the parameters. So when you are going to do this process, iterative process, you are not going to do it for each and every example over there in each pass, right? So what is happening here? You are going to use, when you say SGD, actually you say, okay, just one. But if you're going to do it just one, then how you are going to adjust your weight? So usually, so what happens that we are going to make use of a subset. So that is how it is called mini batch stochastic gradient descent. So instead of giving the entire data set, you are giving a small batch from that. Okay. See that here. See, understand here. Now you need to update this weights. What I am saying that when you are following this gradient descent process, see here you are giving each sample. So in one pass, you are passing on each sample over there, and then you are getting this. Every time you are going to add it, and then you are getting it. So if you are having these many parameters, high parameters, so the cost will become huge. So what is being said that, so if you go with this traditional gradient descent, you need to do it, right? So what is the solution over here? There is another this thing, okay, in one pass, just to give one sample. That is stochastic gradient descent. So you can see that these are the two extremes. In one extreme, you are giving every sample there in each loop, right? And in one, you are giving just one sample. So both these are the extremes. So what is there? We are going to settle up somewhere in between. So we said that instead of giving this whole 3 million, let us say you are giving 1000, right? So that is what is mini stochastic gradient, right? Descent. And I will tell you how, why this works. So that is what we are going to discuss now. So when we go for mini batches, actually it is a good idea. Why? Because now you just imagine, because I showed you the process, that the optimization using gradient descent is very expensive, especially when you are using large data set, right? 3 million, 4 million, like that. So what we are going to do, we are, instead of using all the entire data set in one go, we are going to compute these derivatives and their average values by randomly sampling a small number of examples from the data set. Not going to do it for all, right? Just pick a small number of examples and do this. Okay. And then we are going to take average. See, that is what earlier we were going to take the average of derivatives of loss function with respect to all. Then we are fixing it up. But here we are going to take it only for that small set of uh, uh, in, inputs. So what we do in reality, we divide the entire data set into small subsets, which we call as mini batches, right? So that our training and optimization process may be speed up, right? So you can consider this example, and that will tell you, this example will tell you how this mini batch will work well, right? Because don't believe unless you have some information about it. So you say that, let us say we are considering, because we need to, ultimately we need to take mean of that, right? Whatever values we are getting. So, so let us say if I am going to have this standard error, this error depends upon, so this is the standard deviation from the data which of your samples, right? And so how this error depends upon your data which you are using, that is square root n, in that too in the denominator. Now just imagine your n is 100 and your n is 10,000. Yeah, yeah, do you get? N is 100 and n is 10,000. So second case requires 1,000 times more computations than the first case. 100 hai or 10,000 hai, right? So if you want to know how many times it is going to run, then you say 100 times difference is there. But in the performance, you can see what is happening. In the first case, you get 10. In the second case, you get. So in the performance, like if you, it is very sensitive, just you go very near, it changes. So now here you can see that square root of 100 and square root of 10,000, right? So the performance here, the difference is only of the factor of 10. But getting the performance, the factor of 10, what we need to do, we need to run it 100 times. You can understand, to get 10 rupees, we need to spend 100 hours, like that. Okay? So that is how we say that mini batches, it will work well. And now let us explore more into it. So now, with the mini batches, what will be the worst case scenario? See, we when we say that gradient descent, we are giving the entire data. We say that all entire training space, right? I mean, whatever there, we are giving examples from the entire training space to train my model, so that next time my model is seeing anything, because I'm giving examples from the entire space, so it is going to work well. But what happens in the worst case scenario, it may happen that if we are choosing m samples in a batch, all those m sample are identical copy of each other. Do you understand what will happen? My network is not going to learn. Like, it is just like one example. See, if I'm choosing a mini batch of size m and all those samples are same, it is like I'm just using one sample, right? So that is what the worst case. But what happens in practice, this doesn't happen, right? But on the other case, you say that if you use a large number of example, then also what will happen? See, over. Then what is happening? If you are using large number of example, it may happen that it is going to give you almost same value of gradient, right? So in fact, the repetitive computations on the large data set, they will not be of much use. So that way your mini batch is much useful. So mini batches are particularly, are usually better than your SGD, where typically we say SGD means single example we are going to use. So mini batch, a small subset. Okay, so this is better than SGD. How? Because here, as compared to gradient descent, less computation is required to update the weights instead of entire. You are now using just a small subset, and then you can take full advantage of GPUs. So yesterday, like if you go, because from so my transformation is from computer graphics to image processing to this. So when we did computer graphics, then we know there's transformations, right? That is how the video games and all. So that is possible with your GPU, right? So the GPUs, we can make use of the GPUs here to compute the gradient for many batches simultaneously by using the matrix multiplication, which are very efficiently can be done. Okay. So now, when we are going to apply mini batches for large neural networks with very large and, you can say, highly redundant training set, it is always preferred to go with mini batches, right? And suppose, let us say you are having this M training examples, right? So you are dividing this set into this capital M subsets, let us say of the same size, which you are calling as mini batches. And then we are going to pass each mini batch through the network epoch. Please note, fit it in your mind, right? Because you will, when you are going to study, you will find these terms, right? So just try to fit in all these terms. Okay, so epoch. So you are passing each mini batch through a network, that is one epoch. Now, so what is happening here? You need to apply forward and backward propagation, update the weights, and iterate this process for all mini batches. not for the entire, but all mini batches, right? Now, how do we process, how do we do processing with the mini batches? Remember, we need to guess the initial learning rate. Hmm? Uh, Now, if your error goes up or there are oscillations, right? You want to move straight to the minimum, but there are too many oscillations, then what is happening? You need to reduce the learning rate. It means that you are not going, I mean, from moving one to other place, lot many jitters are there. So that is to be avoided, right? So you say that if the error when you are, because see, nobody will tell you. I think yesterday there was a question also, how to, because these things you need to set and you need to play with it. This is one of the hyperparameter. So you need to play with this. So how do you play with this? So based on the experience, you just take some value and then, I mean, you may adjust it. How you are going to adjust it? You are going to adjust it by looking at the error values. So if your error goes up or it shows the wild oscillations, then you are going to reduce the learning rate. If your error is decreasing slowly, it means you can increase, no problem. So this is there. So see here, you can see this okay. So either you are, see, we are not going for this full batch. Now you can see just one for one. So you can see one batch, how much jitter is there. And then for full batch, how you are moving over there. So you know that when we are talking about how we are going to learn the learning rate, remember that in the literature there are several methods, right, which we can't cover here in this time. And what should be the size of the mini batch, right? This is also a concern. So because see, this size, okay, yeah, small m was the size, yeah. So if the size is 1, then you can see how it is reaching. This is your minima, right? How it is reaching towards there. So the mini batch size must not be too small. It must not be too large. So usually what we do, we typically keep mini batches in this size, right? 64, 128, 256, like that. Now see what is the effect on convergence with the mini batches, because now you are working with the mini batch. So let us say this was my gradient descent when I am using the entire batch, right? All 3 million samples I am using, right? Then this is my, this is how my cost function is decreasing when I am doing iterations with the full batch, right? Now, if I am going to do with the mini batch gradient descent, then what is my cost? You can see what we want. We don't want this much jitter, right? But this is there because we are not using the, we are using a small batch only for training, right? So this mini batch gradient descent, you can see that the cost, like it is going down, but this is how it is going down. And so we can see that these fluctuations, right? So although you can see that these fluctuations are there in the cost, this cost graph, because the samples in one batch may be having different characteristic than other, right? Because you are choosing the batch, it is the different batches, they are having different characteristics, and therefore, I mean, you are converging in this fashion, right? Because of this, that these jitters are there. But rest assured, what is observed, but your algorithm is learning faster by this way. So now the question comes that how are you going to sample the mini matches? Because as I told you, if you are, let us say all m samples are same, then it is not going to serve you any purpose. So how you are going to do the sampling of mini batches? So we say that, okay, we will go for random sampling of mini batches, right? So here you can see that if you want to compute an unbiased estimate of the expected gradient from a set of samples, then your samples need to be independent. If you are using same samples, then what new your network is going to learn, right? So you should have the different samples, right? So we say that, remember when we go for this generative AI, right? So we say that we want to generate the samples. Let us say I'm going for this medical image processing, right? So we were working on this fundus images where we are working on the diabetic retinopathy. right? So diabetic retinopathy, on the fundus image, there are these veins and also hemorrhage and all those cotton wools, all those things are there. We want to identify those small vessels through which the blood flows. And because that flow actually tells me about the presence of the diabetic retinopathy. Now, those vessels are very fine, right? And unfortunately, we don't have much data. So, very small, like for classification of in the class, let us say the data is there. But if you go for the segmentation, because I want to segment those veins, right? So then we don't have sufficient data. So we went for this generative AI. Now the samples, you take example in any, this is just one example from my domain, right? You can take example from any domain. So when you are going to generate a new sample, what we want? We want the sample to be from the same space, but different from the existing sample. So somewhat you can say, if this is my sample, I want to generate from this space only, but slightly different, right? So because if I am going to generate exactly same sample, right? Because we say that we are generating sample, but if the generated sample is exactly same as the, I mean, sample you have, then what, how that sample is going to help you out, right? So we want some variation to be there, but still this variation should be there within that domain, right? Not outside that. So that is how. So there are different parameters on which we are saying, okay, these are the samples we can use. Because when you go for the sensitive applications like medical image processing, or you can say biometrics, when you are using, because if you need to, I mean, it is very difficult to get data for, we prepared one multimodal biometric device in our lab with some BRNS project. Then we need to validate it, and then fortunately I got this data from some students, because we are using cancelable biometric, so there was no problem. We have actually transformed that biometric, and so their original biometric was discarded over there. So I mean, that way, but still some sensitive applications are there. So how to get, because if you are going to get the wrong data, then ultimately everything is going to be in vain. So here we want the estimate to be two subsequent gradient estimate will be independent only when your those mini batches will be independent of each other. So but what happens when you go for a particular data set, that will be naturally correlated, right? So for example, if you are taking these video frames, right, in a video, when you are going for this object detection in a video, so all frames, we all know that how this hand is moving. So basically you are moving like that, right? So every frame is related with every other frame over there, right, in the local region. So what to do? So remember that it is necessary to shuffle the samples before selecting every mini batch, right? Otherwise your algorithm performance is going to be compromised. Now here comes a very important thing, and especially to my students, I would like to remember, because this is something they forget. That is my experience from our class, that there are parameters and there are hyperparameters. So what are parameters and what are hyperparameters? So parameters are the values those which are learned by the model during the training, right? And what are the hyperparameter? Hyperparameters are the external settings which are chosen before training to guide the learning. Now, can you give me one example of the this parameter and one example of this hyperparameter? We are just talking about, you can give example from that only. Yes. Okay. So many, not one, so many. Like I told you about learning rate, that is a hyperparameter, right? How many, like he is saying, how many layers you are choosing in your network, that is also a hyperparameter. In one layer, how many neurons, right? How many units you are choosing, that is also one of the hyperparameter. So always remember, when we talk about parameters, so weights and bias, they are the parameters which actually your model is learning throughout this training, right? During this training process, at this is these parameters, right, weights and bias, they are actually updated automatically through the back propagation as well as optimization, and this parameter determines how fit your model is, right? So basically the model is fitting to the data based on these parameters. Now, what are hyperparameters? External settings, right? So there are so many, right? Number of layers, number of units per layer, activation function, loss function, learning rate, regularization. I will tell you about regularization, optimizer, number of epochs. I just told you mini batch size, right? All these are hyperparameters. You can understand the difficulty over there, right? What to do, what not to do. So we need to set these hyperparameters, and we need to tune them before starting our training, right? And so because these hyperparameters, they are actually controlling the training process as well as the model performance. Okay. So now just see the effect of some of the hyperparameters. Here you can see that if you are using in a layer, if you are using 3 hidden neurons, or you are using 6 hidden neurons, or you are using 20 hidden neurons. So you can see that this is nothing but the number of hidden units in a 2-layer network. So we have just taken one hidden layer and one output layer. And then in the hidden layer, you are using 3 neurons, 6 neurons, and 20. You can see your models, your model is working better. So how this hyperparameter is helping you. Similarly here, although right now you don't know, I'm just going to introduce you regularization. So this is a regularization constant lambda. So you can see that how the value of lambda, I will introduce you very soon. So how this value of lambda you can see is affecting your model, right? So you can see you are decreasing it, and that is how you can see it is becoming more and more sophisticated. So now we come to the optimization in the neural network. And so when we talk about the mini batch gradient descent, then we need to actually optimize it. You say, and then a few optimization algorithms are existing which are actually faster than the gradient descent. So this is just one choice, and then we are having more like gradient descent with momentum, RMS props, then ADAM optimization. So I mean, usually this works well. So I mean, ADAM optimization. Now it comes how why from the mini batch gradient descent, which was working very fine till now, and we are moving towards the other algorithm. Remember here that mini batch gradient descent is an alternative where we are dividing whole data into mini batches. But so that is why it becomes faster than your batch gradient descent, and it also provide you opportunity to update parameters after each mini batch. But there are certain challenges with the mini batch gradient descent. What are these challenges? First challenge is how to choose the proper learning rate. Second is the same, because what happens once you have fixed up this learning rate, see, the parameters are being updated. Hyperparameters, right? Hyperparameter is fixed, that is fixed, right? So if you have fixed learning rate, I mean, it is fixed, right? So you say that if I have chosen some learning rate, then the same learning rate will apply to different types of mini batches, right? And so now the question comes, let us say if you stuck up in the local minima, what are you going to do, right? That is, so if your surface is having ups and downs and you are stuck up in the local minima, you will never be able to get out of it. So that is how there are several other algorithms. So you can say that gradient descent optimization algorithms are applied, which are RMS POPs, ADAM, and all those. Now see, this is what I'm talking about, this local minima. So you can see that if your surface is highly undulated, right? So you can see that if you just stuck up here, right? This is your local minima, but you just stuck up here and gone, right? So to avoid this situation, what is being done? What is being done here? A fraction of the past update vectors is combined with the current update vector. So what happens here? We are going to make use of a momentum. See, for example, if you are going on a road, you are going on a road very fast, but when a turn comes, you need to control your speed. But here, if you see the mini batch example which we have taken, we have fixed learning rate. No matter you are on which road, right? No matter you are on the flat road or you are on the corner, you are going with that speed only. So you want to put some brake to that, right? So you want to have some changes over there, some control over there, right? So here, if we are going to do that up, as I told you, optimization, that is going to increase the momentum for dimensions where gradient points in the same direction, right? So what is happening? Let us say if you are moving too fast, then some brake may be there, right? may be applied there with the help of this momentum. And that is how this optimization, this algorithm work, and they give us faster convergence and reduced oscillation if you are going to follow those optimizations, right? So, so this is what I told you. So right now I am not going to cover it, but if there will be time, then maybe with the CNN I will cover it. So now come to the next word, that is regularization, right? So now remember what we want? We want to reduce the generalization error. Hmm? So any modification which we are making so that we can reduce the generalized error, remember, not the training error. We are saying that we want to reduce the generalized error, right? So any modification that we can make, that works for us, right? So regularization is a method which prevents overfitting, or you can say it helps in optimization. And especially how do we do this? Additional terms are introduced in your objective, right? Additional terms are introduced in your objective to prevent the overfitting or to help in the optimization. Okay. And so that is what your deep learning, like what algorithms, they actually wish to get solution for a wide range of tasks. And so that is how they are using very general purpose framework of regularization. There are several schemes, right? There are several methods of regularization that I am going to tell you now. So this is your loss function. This is your data loss. Now you are fine with this, right? So this is your loss, and then so with this loss, your model is predicting, right, how your it is matching with the training data. Now what we are doing here, we are going to add, see what I said, that we are going to add on some terms in the this optimization, this loss function. So here we have added this term which is going to prevent the model from doing too well on the training data, because we don't want overfitting, right? Overfitting means that it is working very good on the training data, but not on the testing data, right? So we want to avoid this, and that is how we say that we are learning, and for this learning we have added a term that is nothing but a penalty actually. I mean, we are imposing a penalty over there, and this penalty is called regularizer, and which we are adding to the cost function. So this is the penalty we are adding to the cost function, and this lambda, remember with that picture I showed you, that lambda, this is that lambda. So lambda is nothing but the regularization strength. So we say that this lambda here, we are choosing this lambda to control the strength of our preferences for the small weights, right? Now, so when we, as I told you, there are many regularization methods. So here you can see that so many regularization methods are there: L2, L1, data augmentation, multitask training, early stopping, dropout regularization, right? So many. But remember that no matter what is your regularizer, the ultimate purpose of the regularizer is that to reduce the variance, right? Because if you are putting up the different training examples, so reduce the variance significantly, at the same time maintaining the low bias. That is what we want. Remember our first thing, we started with the generalization of the model. So we said that bias and variance. So we want to keep both low, right? But there was a problem in maintaining both low. So we are saying here, by using, what is the task of the regularization regularizer? To maintain the low bias while reducing the variance. Now see this example. So let us say this is my input, and these are my weights, right? So the two set of weights are there, W1 and W2, right? So let us say I'm saying W1 because weight Wx, right? That is what we are doing, Wx plus B. So now it comes, let us say if I'm choosing L2 regularizer, then given a choice, which weight will be considered? If you are choosing L2 regularizer, given the two set of weights, right? Whether you are going to choose, with L2 regularizer, W1 or W2. Now remember that this L2 regularization likes to spread out the weights. Now I think you can give the answer. And I am telling you that L2 regularizer spread out the weight. So it is very clear which weight it is going to choose, W2. Right? Now come to the data augmentation. So remember that, because we are having your deep learning models, they work good when you are having good amount of data, but how to get that data? So data augmentation is another technique which is used to improve the performance. Now what do you mean by data augmentation? Basically, along with the images, we are introducing more images. How we are introducing more images? They are nothing but the transformed version of these. Like, so which transformations? For example, this picture is a rotated version of this picture, right? Similarly, this picture is a cropped version. You have cropped it from here. This picture is where you are going to, because the noise, right? It should, so you are adding the noise, and that is how. So along with the data, you are using these samples, right? Corresponding to your data, you are generating these samples, which you are using for training purpose, right? That is your data augmentation. But when you will go for data augmentation, then you have to be very, very careful when you are adding noise, or when you are using rotation or flip. Because when you are doing the flip, your 6 becomes 9 and 9 becomes 6, right? And ultimately your model will take it wrong. So now there is another concept, early stopping. All these are buzzwords. When you will work with your network, you are going to, you will come across. So what is early stopping? See, when we go like we do not stop like as we do in the traditional optimization process, that your training algorithm is going to stop at the local minima. So we do not wait up to going to the local minima, right? What they say that, okay, whenever this early stopping criteria is satisfied, just stop. No need to go towards the achieve the actual local minima. Just stop when this early stopping criteria is fulfilled, right? So this early stopping criteria is actually based on loss function, which is based on the validation set. Just a minute. So this criteria actually going to stop your algorithm just before the overfitting is taking place, right? Because overfitting we don't want. So just before the overfitting will take place, this criteria is going to stop your algorithm, right? What does it mean? It means that we are actually approximating. We are not getting the true loss function value. We are actually approximating the true loss function in the learning process by giving experience of validation data to my training algorithm, right? Not exactly, but I'm just giving it this, right? So that is how you can see here. This is your generalization error, right? Now you can see this is the error is too high. So basically this is the underfitting zone. Here you can see the error becomes low, but again you can see it starts increasing. We do not go to this say. So you have to stop, right? Let's say. So this is the optimal one, early stopping. Please stop, don't move towards, right? Because again, you can see the variance is increasing. See the way, because we want both bias and variance to keep low. Now, so what happens here? Again, the same thing is shown with another picture. So when you are training your large model, just a minute, I need a pause. रिकॉर्डिंग ही स्टॉप करनी थी उसका यूट्यूब पे उसको पॉज करना. Okay, you can start. So now, when you are going to train large models with there is, I mean, there is might be an issue of overfitting, right? Overfitting. Then it is observed that your training error decreases, right, steadily over a period of time. You see now, this is your training error. But validation error starts increasing, right? That is what I was showing you in the previous slide. So before that, validation error start increasing, right? See variance. Before this variance start increasing, please stop, right? So this is what is early stopping. So stop when you are having good validation. Now there are some more methods, dropout. So in each forward pass, what we are doing, we are not moving forward with each and every unit, right? We are saying that in each forward pass, we are randomly setting some neurons to 0. Okay? So what happens here? And I mean, the probability of dropping is again a hyperparameter, right? That, okay, there is a 50-50 probability that this neuron will be dropped. So here you can see that this is the, on the left hand side, this is the standard neural network, and on the right hand side, this is after applying the dropout. So now this basically dropout regularization, it is computationally inexpensive but a very powerful method when you are going to regularize a broad range of models. And here what do you do? That at each training, right, at each iteration point, you are going to retain each unit with a probability p, right? So 50-50, right? It may be kept, it may not be kept, like that, right? So, and but at the test time, the network is used as a whole, right? And the weights are scaled down by a factor of, because now we are going to use the entire network. So remember that dropout trains, uh, with the help of dropout, you can actually go for very large network, right? Because when you are going to do your, and here what is happening, instead of you will say ki we are dropping, then why not we are taking less number of units? See, it is not like you are dropping every unit every time. Sometimes some unit will be dropped because every unit is having some probability, right? So it is not like that it is totally off from your scene. So here you can see that this is the scenario in the training, and this is the scenario at the testing. So in the training, this unit is present with the probability p, and in the testing, this is always present. Uh, Equally effective is there, that is inverted dropout. Now you can see here p, and what we are saying, at the training here, each weight is scaled up with a factor 1 by p. So that, and at the training, sorry, at the testing, no scaling is applied. See the difference over here, this, right? And then here in the inverted dropout, see, you are already, when you are doing the training, each weight is scaled up with a factor 1 by p, and at the testing, we are not applied any scale. So usually what happens, that for input layer, the probability is more, because I mean we want to keep more inputs over there, and for hidden layer, probability is usually kept as 0.5. Now how this dropout affects to the result. So these are the experimental results shown here. So on the MNIST data set, and this is you can see that without dropout, see, without dropout, this is the scene, and with dropout, this is the scene. So here you can see that I showed you example also yesterday, that each layer, at each layer you are learning something. So let us say you are learning edges. Okay, so here you can see that here you are able to learn, right? The this is the result when you are taking dropout probability as 0.5. So here your units are able to detect the edges, strokes, right, spots in different parts of the image. But here this is not, right? So here you can see that no dropout is there. So these units have actually co-adopted, and here you can see that these units, they are not able to see some random points, right? But here you can see clearly that it is learning. Okay, so here you can see that without dropout, this unit actually tends to compensate for errors in other units, right? So because there is some error in some other unit, and it is compensating for that, right? So because of that, it results in overfitting, and that is how it is not learning, right? So you can say that. But dropout, I mean, the other layers become more, I mean, uh, it is actually presence of other layers, it is making this hidden units unreliable. So that is how in the presence of dropout you can learn in a better way. So this is another this thing here, this example, test error is shown for different architectures, and with and without this dropout. And so here you can see that with dropout and without dropout. So that is how the dropout helps us in implementation. So dropout benefits, there are, I mean, I already told you, scale free, and dropout does not penalize the use of large weights whenever it is required. And it is also invariant to parameter scaling. Now, in the dropout, you are dropping some of the units, right? Here it is drop connect, another scheme. Another regularization scheme is drop connect, where you are dropping some connections. Here you can see that all units are there, but you are dropping some connections. Now, so finally we have reached here. So I told you about all those terms which we are using in the neural network. So just remember those. And so here you can see that whether it is a one layer, two layer, whatever your architecture is there, there are several design issues because your deep neural networks, they typically have many layers and millions of parameters, right? So remember that even if you are having a very basic neural network, right? Not we are saying that very big, right? Very deep neural network. Even if you are having a very basic network, then also there are many design decisions to make. What are these? Number of hidden layers, number of units per hidden layer, right? So you can say depth, number of hidden layers, then width of each, in each layer, how many units you are using, types of activation function, what sort of non-linearity you want to introduce, then a form of the objective function, right? Loss function, learning rate, regularization, optimizer, right? Epochs, mini batch, and all those things. So see, even if a small network, you need to do with all these things, right? So when we go for deep neural network architecture, we have many there, many architectures are popular, and you must have heard also. So maybe tomorrow we will tell you about convolutional neural network, one of the most famous ones. So I mean, what happens, this whole thing which is started in when this ImageNet data set we were talking about yesterday, Fefeli and her group, right? They came up, and then this competition is started in 2012, and the LXNet came. So basically, this when this deep learning came forward, then this convolutional neural network, they you can say that they actually um, incarnation, you have the word. So basically it is CNN which has it does the incarnation of the network, right? So we'll see how the convolutional neural network will work. And so this is, so when we talk about deep learning limitations finally, so unlike humans, it needs large amount of data to learn. That is one of the shortcoming. And remember always that if the test data characteristic is not same as the trained data, then your deep learning model will not give you good performance. Always remember this. So in other words, you are saying that we are learning so much, but we are saying that deep learning is actually a shallow sort of learning, right? So it is a shallow, and because the algorithms are good at memorizing. For example, what we do it here, right? You have remembered something, so you are giving answer to that, but when some applied question comes, then it becomes a problem. So same sort of situation is there. Deep learning is shallow, so it works like a black box. So you can say that now I showed you how this W1 is affecting loss function, how W2, now remember, understand millions of parameters. So it is very difficult to I mean understand, right, to tell what exactly is going on over there. So we can say that it works like a black box, and there are so many things which are affecting the performance, and that is why nowadays the research, the focus of the research is on explainable AI. So you must have heard the word. So when even if we are writing the papers now, we are submitting, so this question is being asked, why so? We need to answer that, how this architecture, why these layers, why this, why that, I mean, how it is giving you good. So we need to explain, right, how our results are good, or this explainable AI thing is there. So always remember that dealing, no matter we are having this computational power, but still dealing with very high dimensional data um, is always a problem. Theoretically it is okay, but still practically it is a problem, right? So that is, so these are the references. These are various slides. So हाँ कोई बात नहीं pause so I think I so So I think Steve has already given you that he has uploaded all his material on a GitHub. So I will also upload my slides over there. So you will get it from there. So if there will be, so if there is there any question or we should call it off for and go for yes. Mhm. Hinge point. Gradient descent is always a problem. So what happens that when you are going to apply these activations, right? So when your if your gradient dies out, right? That is why you can see all those optimization is there. So that is what I did not cover. So we used to like we used to keep it alive. Mhm. What do you mean by I'm not getting your question actually? Hmm. No, no. Input parameters are discrete only. Input parameters we are giving some values to them. Our activation function, which we said that must be differentiable. We are giving values to input parameters. No? So those are the discrete values, not the continuous value. Mhm, 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 mhm. See, corresponding to any input, when you are saying going for output, so corresponding to classes, you are giving a number only. There is not 1.1 or 1.2 or 1.3, right? So you are giving those classes. So what is happening that the class at the end of the day, I mean correspond. Let us say you are using your data is of belonging to 10 classes. So at the end, at the output layer, what happens? Your softmax layer that we'll discuss. So it will give you the probability of all those classes. Now the highest probability that becomes the class of this data. So how do you represent this? You just actually tell this by keeping when this one hot encoding. So you are keeping all whatever class is there. You need to train that number set to 1 and remaining for all classes 0. And at the end of the day, it is generating probabilities. Then the highest probability that class. Yes. No, no. I showed you the example over here. See, I showed you the example of the dropout, how the presence of the dropout is helping you. Because what happens that if you look at there, without dropout, what is happening? These units, they are actually compensating for errors in the other units. So if there, see, there, we are ultimately considering this whole scenario there. So someone is facing problem because of the other. right? So in case there is no dropout, then let us say this unit is compensating for the error which is not done by this unit but by the other unit, right? So if that other unit is taken out, then I mean slightly, it's maybe slightly better. See, what is happening? One way is that you are keeping it low number, but low number is not serving you a problem. So you need more. When you are needing more, then one is, I mean, there might be some might not be working that good, but some may be good. So instead of taking it always out of the system, what we are saying that because for the different examples, the behavior will be different. It is not like that if I'm giving 10 example and all units behavior is same for all those 10 examples, right? Maybe for some examples this unit is doing good, for some examples this unit is bad, doing bad. So when this unit is doing bad, why the other unit, and the other unit is compensating for it because you need to keep that loss function low. So here the probability is 50, right? 50%, 0.5. So we are saying, okay, for the cases where this is creating problem, we are dropping. So that is how it is done. Okay. Thank you.